Welcome back, friends. So, we were looking at the Klein-Gordon equation and encountered problems with the Klein-Gordon equation solutions. The solutions, there are two solutions instead of one solution essentially. Compared to the non-relativistic case, we have in the relativistic case it is always a multi-particle solution, essentially it has two solutions. And the second problem we encountered was with the probability density. The probability density, if we compute it in the relativistic case, is also has a time dependent factor, because all the time and space are considered to be in the same footing in the relativistic case, and so you end up having situation in which the probability density could be negative. Okay. So, you can, the initial condition should be chosen such that the probability density could be negative. Now, so in the relativistic case, the interpretation that the rho should correspond to probability density should not be no longer used. Instead, so this rho should corresponds to electric charge density containing both positive and negatively charged particles. So then it makes sense, because you can have a situation in which there could be both negatively charged particles, and there can be a situation in which there could be more positively charged particles in a given system. Okay, the interpretation that it is the probability of finding a particular particle in a given space time is no longer valid for the rho in the relativistic sense. So, the rho should be more corresponding to the number density of a given with a given space time volume. So, around it essentially the rho corresponds to number of particles versus number of antiparticles, and antiparticles will have electric charges which are exactly opposite. As we have seen, they have the same mass and the spin of the particle, but have electric charge which is completely opposite essentially. So, today what we will do is we will continue with this interpretation to make sense of the Klein-Gordon equation essentially. Okay. So, recap, so I will just start with again writing down the Klein-Gordon equation, but before that I want to introduce something called the Klein-Gordon Lagrangian, which will be useful more when we encounter something called the quantum field theory, which will be quantum field theory, which is the actual subject. So, after which we have one has to deal with for relativistic systems instead of relativistic quantum mechanics or quantum mechanics in the relativistic framework. Okay. So, the Lagrangian is Lagrangian density L, okay, density, okay, as it is called in the relativistic framework, okay, and the Lagrangian is typically Lagrangian density L of say x dot t in classical mechanics essentially. Okay. So, let us start with maybe let us start with classical mechanics. In classical mechanics, Lagrangian is a function of x dot and t, or q dot and t essentially, okay, whereas the Hamiltonian is a function of q, or okay, this also can be written as q, which is a generalized coordinate, as t, and q p. The Hamiltonian is a function of, oh god, q p and t, the Hamiltonian. So, we have these two functions, Lagrangian and the Hamiltonian, in classical mechanics. Okay. In relativistic field theory, you will why this is important you will see in a few seconds, just bear with me, because I want to give the interpretation of how the current interpretation that this is equivalent to the electric charge density interpretation comes for the Klein-Gordon equation. So, for that we need to introduce a few things which are important essentially. Okay. This is in classical mechanics. So, in classical mechanics we are very well aware of these two functions which are called the Lagrangian and the Hamiltonian. In relativistic field theories, you can construct Lagrangians out of. Okay. So, what is more important is something called the Lagrangian density, because the action in non-relativistic theories is nothing but non-relativistic theory LDT essentially, but in relativistic field theories the action is L x mu dx mu. Okay. Now, instead of x mu's, what you can use is essentially the fields itself will be the variables. So, the Lagrangian density would be phi, phi dot and t. Okay. Phi is any field, essentially any scalar field. Essentially we will come to more complicated cases with fermionic fields in the next set of lectures, maybe hopefully starting soon, essentially within 1 or 2 lectures. So, these instead of x you use the field itself essentially. So, the scalar field itself. Now, I am using, so far I have used the word wave function for phi. Okay. Now, I have just shifted the entire interpretation in one shot by calling phi to be a scalar field essentially. Okay. Because in reality the Klein-Gordon field or the Klein-Gordon phi is not really a wave function, but it is a scalar field essentially. Okay. It is not really a wave function, it is scalar field. Anyway, so we will touch once in a while the field theory concepts. Okay, we will not be doing completely quantum field theory. So, we will be just only touching those concepts which are important for us essentially. So, why I am introducing the Lagrangian density? The Lagrangian density is a function of phi, phi dot and t such that I need to get the Klein-Gordon equation applying Euler-Lagrangian equations of motion to the Kg Lagrangian. So far how we derived the Klein-Gordon equation is just by imposing quantization conditions in the relativistic framework essentially. But you can also derive the Klein-Gordon equations by using the Lagrangian or the Hamiltonian formalism essentially, and this makes it easier for us to introduce interactions essentially in the relativistic sense. Okay. Now, only then we can actually, as you will see essentially, that only then you can interpret what is an electric charge and what is a current and everything essentially, why there is a current and everything. So, what I am trying to give you here are glimpses of field theory. I will not be able to cover you the entire aspects of field theory. So, these glimpses are important to understand the interpretation of the Klein-Gordon equation, and then we will see other aspects of the Klein-Gordon equation. Okay. So, for that I need to introduce something called the Klein-Gordon Lagrangian. The Klein-Gordon Lagrangian, so if there is a Lagrangian, I should get back my Euler-Lagrange equations, okay, which should give this is the Lagrangian should be in such a way L Kg should be give you the Klein Kg equation after applying the Euler-Lagrange's equation. So, that means delta L kg by delta phi, or what are the variable essentially, del mu by delta L kg by del of del mu phi whole in del phi is equal to 0. So, if I do this, I should get back my the variation with respect to the field itself, or the variable of the Klein-Gordon Lagrangian, and the variation with and the subtraction with the variation with respect to the derivative, the 4 component derivative of the field. This is what we want, and this should give me back what is my kg equation. This you can derive it yourself essentially, and I can once I give you the Klein-Gordon Lagrangian essentially. The Klein-Gordon Lagrangian is easy because you can write it down, is equal to del mu phi dagger del mu phi minus m square phi dagger phi. Okay, this is the equation, and now once you apply, this will be left as a homework and it will be given as a homework problem. Once you apply the Euler-Lagrange's equations, you will get back your Klein-Gordon equations, which is nothing but box phi plus m square phi is equal to 0. So, you can apply your Klein-Gordon equations for this essentially. Now, what should be a Lagrangian be? The Lagrangian should be Lorentz invariant, because we are dealing with relativistic theories essentially. So, the Lagrangian should be Lorentz invariant and it should be real. These are the two main constraints on and it should be a Lorentz scalar. Let us say, because it should be a Lorentz invariant, it should be a Lorentz scalar. These are the main constraints on the Lagrangian. So, this Lagrangian consists of this what we called as a wave function now is being called as a scalar field essentially. That is the only thing, the difference between okay, and you give a Lagrangian form. Okay. Now, I can now this Lagrangian formalism is why it is useful essentially, because then I can ask covariantly in a, now you have another covariant theory, a theory of electromagnetism, okay, another relativistic is the theory which is the originates of all relativistic models, is relativistic theory is theory of electromagnetism. I will just write it as EM. Oh God, oh wrong pen. Theory of electromagnetism. What is this theory? This is the theory which in the classical sense is nothing but theory of Maxwell's equations essentially. So, this is nothing but this is a theory of Maxwell's equations, which we all know. We know that you can write the Maxwell's equations in the covariant form by using the F mu nu tensor essentially, the electromagnetic tensor F mu nu. So, this is nothing but electromagnetic tensor field strength tensor. Now, this has a form F mu nu has a form in terms, it is an antisymmetric tensor, it has a form in terms of the electric and magnetic fields. Okay. You have to fill up this form, okay. This is also something which I will leave it as an exercise. So, this is this has an electromagnetic form where the F0I components correspond to the electric fields and Fij components correspond to the magnetic fields essentially. Now, if this is the case, so that means you have these components which are electric fields and these are components which are magnetic fields, but you can also express this entire thing in terms of the vector potential A mu. In this sense, the vector potential F mu nu, in terms of this vector potential F mu A mu, the field strength tensor is given in terms of del mu A nu minus del nu A nu, which is nothing but the antisymmetric combination of the derivative vector and the vector potential essentially. Okay. So, this is nothing but the antisymmetric combination of the derivative vector and the this thing the vector potential essentially. So, the entire theory of electromagnetism is given by this. Now, what is the Lagrangian corresponding to this? The Lagrangian corresponding to this is called LEM is equal to minus 1 by 4 F mu nu okay. This is the vector this is F mu nu trace of the F mu nu square essentially F mu nu square, in which nu and mu are summed over essentially. Okay. It is the antisymmetric tensor and with the up and with the minus signs reversed essentially you have the other matrix and you take this sum over all the indices, you end up having this particular form for this electromagnetic Lagrangian. From this you can get back the equations of motion, okay, but for the equations of motion, okay, for the electromagnetic current as del mu F mu nu this will give you in the classical sense two electromagnetic two of the Maxwell's equations, and there is something called the dual tensor. The dual tensor F tilde mu nu is equal to epsilon mu nu rho sigma F rho sigma, and the equation of motion corresponding to this will give you Maxwell's equations in free space where there are no sources and currents essentially. Okay. These two set of equations will give you Maxwell's equations. Okay. Just to revise ourselves before going further. So, what we have is essentially that I introduced the concept of Lagrangian density, and we are moving a little bit ahead because we are going into the regime of quantum field theory, in which but we are not going to do the full quantum field theory, but we are only going to use the concepts of quantum field theory such that we understand what is the meaning of the Klein-Gordon equation, how do you say that it has electric charge +1 and -1, and that is the reason why essentially how to understand that part. For that particular reason we introduce some concepts of quantum field theory which are essentially using the Lagrangian formalism. So, we introduce what is called the Lagrangian, in which the wave function phi of the Klein-Gordon wave function has been moved to called something else as a scalar field, is called something as a scalar field. So, it has also as a just like electromagnetic field, you also call the phi as some scalar field, but that phi will be quantized essentially, and later on as we will see in quantum field theory, this phi can be quantized to give, just like the electromagnetic field is quantized to give you photons, this phi field also can be given quantized to give you particles, essentially one single particle essentially, because you remember that the solutions of this has multiple solutions. It should not be interpreted as a single particle anymore. This entire thing is a multi-particle system essentially in the relativistic sense. Okay. So, it becomes a Klein-Gordon field, and this Klein-Gordon field, so you can write a Lagrangian density. So, Lagrangian density, this should be d power 4 x. So, the Lagrangian density, which is a function of phi, phi dot and x instead of x mu, x dot or q dot and t, phi dot and x, and with the condition that the Lagrangian should give you correctly the Klein-Gordon equation. Okay. So, you have a new way of derivation that the Klein-Gordon you start with a Lagrangian density, which is like the Klein-Gordon Lagrangian, and then use the Euler-Lagrange equations, which are essentially given in this particular fashion in field theory, essentially in classical field theory or quantum field theory, and then this gives you back the, after applying Euler-Lagrange equations, you get back your Klein-Gordon equation. Now good, now why do you need this Lagrangian in the first place, because if you are getting back only the Klein-Gordon equation. Okay. The point is that with the Lagrangian I can now try to learn how to couple this to an electromagnetic field, because electric charge is only defined if it couples to an electromagnetic field essentially. That is the main thing essentially, that is the reason why we are repeating redoing this analysis, such that we have a physical interpretation of what phi and phi star mean. Phi has a electric charge of +1 or phi star has an electric charge of -1. How do you know? Free particles will not have electric charges, right, unless you put it in an electromagnetic field. You do not know what is +1 or a -1 electric charge essentially. So, you need to see how to couple the phi to an electromagnetic field essentially. That is the reason why I introduced the concept of Lagrangian. So, the Lagrangian then, so we look at the Lagrangian of the electromagnetic field essentially. So, electromagnetic field or the electromagnetic theory has a Lagrangian of its own, which is given in terms of the electromagnetic field strength tensor, okay, and which has, it is an antisymmetric matrix, okay, whose form you all know because you have studied relativity essentially. So, but this will be repeated as a homework problem essentially. So, anyway you can look into it up essentially. So, but it also can be written in terms of E and B fields. I have already mentioned it in the lecture once, but anyway you can look it up essentially. So, this also can be written in terms of the electromagnetic vector potential A mu. So, the F mu nu is given by the antisymmetric combination of the derivative vector 4 vector and the vector potential A mu. Now, what is this vector potential A mu? We know the vector potential A bar, which is nothing but the A bar of the classical electrodynamics. In the relativistic electrodynamics, in the relativistic notation, vector potential has a 0 and a bar. This is nothing but your vector potential, and A 0 is nothing but your phi, the scalar potential, the electromagnetic scalar potential essentially. So, these two combine to form a 4 vector, these two combine to form a 4 vector, and then you can re-express your electromagnetic Lagrangian electromagnetic theory Lagrangian as minus 1 by 4 f mu nu, which has equations of motion given by derivative of f mu nu is equal to 0 and derivative of f tilde is equal to 0 essentially in free space. So, there is no current or anything, there are no sources, there are no currents, there are no free charges essentially. Now, let us proceed further to couple this electromagnetic theory. So, this electromagnetic theory also has, so if you solve this essentially, this also gives me an equation of motion for the A mu as del A mu is equal to box A mu is equal to 0. This also gives me these two equations you can always see box A mu. So, this is similar to the Klein-Gordon equation essentially box A mu is equal to 0, and which does not have, there is no mass term because electromagnetic field if you quantize it, it gives you photons and photons are massless. So, this is the equation of motion for the photons essentially photons. When you quantize the electromagnetic field, you get the photons and these photons are massless. So, you do not have box plus m square or box plus something else essentially. So, the mass term is vanishing is not present. So, you only have box. So, box if you remember I introduced you in the earlier classes essentially is nothing but del by del t square minus box nabla square or del square. Okay. Essentially I think I introduced you here itself this one essentially I introduced you what is box essentially. Okay. So, remember that. Now, what we have to see is how does the Klein-Gordon field couple to the Maxwell's equation. So, what we are looking at is the coupling to Klein-Gordon field to the Maxwell's equations, which undergoes through something called the minimal coupling. It there is also an underlying symmetry principle behind it, which corresponds to the charge conservation. So, we will not I will come back to it about essentially. So, the basic idea of minimal coupling is that wherever there is this is exactly like in quantum mechanics. So, we will just like in quantum mechanics. Okay. Mechanics, if you have a particle in an electromagnetic field, what you do is P bar okay, momentum is replaced by P bar minus E A bar, which is the electric magnetic potential, and that is how you write your Hamiltonian. Wherever there is a P square minus P square by 2m, you replace it by P minus A by P bar minus E A bar whole square by 2m, and then you continue working on it essentially. So, the kinetic term is replaced by something called the minimal coupling. So, this is the coupling essential electromagnetic charge and this is the vector potential, which we already introduced essentially. So, what we are going to do in quantum mechanics in the relativistic regime is we will just take the same idea that that there is a minimal coupling also, which also works in the relativistic regime. Okay. So, this is the basic idea here. We will assume minimal coupling to work very well in the relativistic regime also. So, what we need essentially is that instead of p bar what we have in the so we have p mu. So, what we need is essentially, so instead of p bar we need p mu should go to p mu minus I e a mu. Okay. This is basically the minimal coupling definition essentially. This is basically the thing that why you need to introduce something called this is how you couple the photon the momenta, okay, to the momenta to be modified in terms of this one essentially, okay, in terms of the how do you couple the photons with the kinetic terms of the fields essentially of the fields or the what do you call the wave functions essentially. So, now let us remember, let us write down this part, okay, let us write down this part. So, first we will write down your ordinary Klein-Gordon Lagrangian. The ordinary Klein-Gordon Lagrangian is del mu phi dagger del mu phi minus m square phi dagger phi, and then you write down your electromagnetic theory, okay, L E M, which is nothing but minus 1 by 4 f mu nu f mu nu. Okay. Now, we have to write down the modification. So, if you want to put in the coupling between p mu and so the derivative, so the derivative has to change to del mu goes to capital del mu is equal to del mu plus I e a mu. The minimal coupling appears in this particular fashion, in the relativistic fashion. So, what we are writing, this is momentum basis, right, essentially p mu is in the momentum basis, but in the position basis you have derivatives. So, in the Lagrangian, so now you see the reason why I introduced the Lagrangians essentially. The Lagrangians are introduced so that you can have the coupling, this way you can have the coupling between the phi fields or the wave functions and the electromagnetic field essentially, and the electromagnetic field. Now, putting this back into this, so the Klein-Gordon equation, okay, by substituting this by this minimal coupling, introducing the minimal coupling. So, what you have is del mu phi dagger del mu phi minus m square phi dagger phi minus 1 by 4 f mu nu. This is your Klein-Gordon field essentially. This is the Lagrangian of the Klein-Gordon field essentially. Okay. So, let me stop here, and then in the next session essentially I will continue the interpretation of this particular thing and tell you why that tell you to make how it makes it easier now to interpret the current to be coming from to be actually equivalent to the electromagnetic current essentially. Okay, I will just stop here.